All right, so we're going to move on into the second section of Unit 6, which is all about local behavior of polynomials. And what this is focused on is, in the last section we talked about the end behavior, what's happening at the ends, together, opposite, up, down, that kind of stuff. So that was only the ends. Now we want to focus on kind of what's going on in the middle, which is all around our intercepts on our x-axis, okay? So I want to point out a few things. So before I get into this, I just want to refresh because we just got done with quadratic functions, right? So if we had something that looked like f of x equals ax squared plus bx plus c. If we had something that looked like this, we could solve it by factoring, we could get it into vertex form, or we could solve it by doing the quadratic formula, right? But any time that we have an x squared, remember, we were able to get two solutions, right? This might factor into x plus some number d, right? And x minus, I don't know, f. Okay, right? We factored this. Because it was an x squared, we usually got two factors, right? So I just want to show you an example of this. You may have gotten something like x plus 2 times 3x minus 4, right? Something like that. I don't know. It's just specific to whatever function you have. So if you get two factors, then when you're solving for x-intercepts and you set that equal to 0, what you're going to end up with is two x-intercepts, right? This one's going to give you -2, 0, and this one's going to give you 4/3, 0, or something similar to that, right? So the only way that you would not get two intercepts is if you happen to have a repeat of the same factor, right? So we could have something like, maybe when we factor our function, we end up with something like, I don't know, x minus 3 squared, right? We end up with two copies of that same factor, right? Then when we solve this, we would only get one x-intercept, right? So that's one thing to note is when we have an x squared, we're either going to end up with two x-intercepts, one x-intercept. Remember those parabolas that opened up above the x-axis? They had no x-intercept, or the parabolas that opened down that were below the x-axis, they didn't have x-intercepts. So the number of intercepts is very much so related to the degree of the polynomial, right? This is an x squared. We could get 2, we could get 1, or we could get none, right? All right, so I want you to keep that in mind as we move into this next section, because that will kind of help us rationalize some other things. So when we look at our local behavior of polynomials, there's a couple of things we're going to look at. We're going to look at turning points and intercepts. So I'm going to skip all this because y'all can read that. Okay, I'll reference it again here in a little bit. But I want to focus on this graph. This graph is of this function right here, x to the 4th minus x cubed minus 4x squared plus 4x. Notice this is a degree 4 polynomial, right? Whatever that highest power of x is, I'm just going to write over here. This is a degree 4 polynomial, right? Because our highest power of x is x to the 4th. And notice with that same reasoning about x-intercepts, we can look and see how many x-intercepts we have on this function. We have an x-intercept here, we have an x-intercept here, another one over here, and one more out to the side. So we ended up with 4 x-intercepts. So we actually have this little note, or this theorem, if you will, that states that the number of x-intercepts, or the maximum, here it's written, the maximum number of x-intercepts that a polynomial function can have is equal to its degree. Okay, so notice, because this is a degree 4 function, okay, we can have up to 4 intercepts, right? Now, it could be possible that we only have 3 intercepts, or 2 intercepts, or 1 intercept, right? Or no intercepts, if depending on what this factors into, right? But for this specific example, we had all 4. So this is a really important thing to note that will help us work these problems and know how our graph should look, that if we have a degree 4, we should have a maximum of 4 intercepts. Okay, we could have less, but we're not going to have more than 4. The other thing that's important to note is what's called turning points. Now, we discussed turning points just real quick, when we were talking about parabolas. So parabolas that are opening down, they are either, they start off increasing, and then you go up to the vertex, and then they decrease, right? So they look like this. So that is a turning point, the vertex point, because we're changing from increasing to decreasing. So anytime the graph changes from increasing to decreasing, or if it's an upward opening parabola, right? If it changes from decreasing up to increasing, that point is called a turning point. So notice on our example here, it goes from decreasing to increasing. So at this point right here, we have a turning point, right? And then since it's increasing up to this point and then it changes back to decreasing, then we have another turning point there, right? And then we have another turning point when we go from decreasing back up to increasing. So when you look at this picture, the number of turning points we have has somewhat of a pattern also, because the only way that something can change from increasing to decreasing or decreasing to increasing is at these very specific points in between intercepts, right? So between this intercept and in this intercept is when it changed from decreasing to increasing. Between this intercept and this intercept is when it changed again, and between these two is when it changed. So what that tells us is, if we know the number of intercepts or the degree of our polynomial, right? If we know like it's a degree 4 polynomial, right? And we have 4 x intercepts, the only places that we can have those turning points are in between our intercepts. So if we have 4, then the maximum turning points we can have is 1, 2, 3, right? Because that's how many in between places we have. So that's what this note is talking about. A polynomial of degree n, okay, will have at most n minus 1 turning points. So as long as we know the degree of our polynomial, we know whatever that degree is, let's say it's 10, right? Then we could have 9 possible turning points, because it's always one less than our degree of our polynomial, okay? Can have at most 1 less, right? And intercepts, at most, it can have equal to our degree, okay? So we're going to kind of apply this and see how we're going to use this, how this helps us out, okay? So on the next page, there's a couple of examples. So here it says, identify the degree, maximum number of turning points, and the maximum number of x-intercepts. So remember, our degree, we're calling that n, and the maximum number of turning points, okay, is n minus 1. So whatever our degree is, we know we can have up to, 1 less than that on our turning points. And we want to find the maximum number of x-intercepts, which is equal to our degree. Okay, so all of this can be found just by figuring out what the degree of the polynomial is. And like our last example, sorry, let me put it back up here. All we need to see is this leading term, right? Because if we see what that leading term is, we can easily just look at the exponent on the x to determine our degree. Okay, so that's what we want to do on these examples. The only problem is these examples aren't multiplied out, right? I don't have this written out as a polynomial in standard form. So I want to go ahead and do like we did when we determined in behavior and just figure out what that leading term is going to be. So if I look at this factor, right, negative 3x squared is my highest degree term, my only term in that factor. In this quantity here, my highest degree term is x. And in my last set of parentheses, my highest degree term, again, is x. So I'm just going to multiply all those highest degree terms together to figure out what the leading term of my polynomial function is. So my leading term should end up being negative 3x to the 4th, right? And then, of course, there's going to be other terms that come after that, but we only care about this leading term because what we're really looking for is that degree. So this tells me that this is a degree 4 polynomial, okay? So once I know the degree, I know the maximum number of turning points, right? The maximum number of turning points is 1 less than the degree. So that means for this function, we can only have up to 3 turning points, okay? And then I also want to find the maximum number of x-intercepts. And remember, the maximum number of x-intercepts is equal to the degree. So for a degree 4, the maximum number of intercepts we can have is 4. Okay, so this is all the stuff we just figured out about this function. Okay, let's get another one. So same idea on this one. I need to first identify what is my leading term. Once I know what my leading term is, then I can identify all the stuff we found here. So I'm going to take the x cubed. I'm going to take the negative x, right, because that's the highest degree term in this quantity, and the highest degree term in my last quantity is 2x. So I'm going to multiply x cubed times negative x times 2x to figure out what that leading term of this function is going to be. So when I multiply all that together, I'm going to get negative 2x to the, let's see, 3, 4, 5. So negative 2x to the 5th power. Okay, and there's going to be other stuff that comes after that. But we don't care what it is because we're just trying to figure out the degree. So now that we see the power of x, we can go ahead and state that the degree is going to be 5, which means that the maximum number of turning points that we can have for this function has to be one less than that, so 4. And our maximum number of x-intercepts is equal to our degree, so the maximum number of x-intercepts we can have on this one is 5. Okay, we kind of okay? All right, so I wanted to give you some problems that are similar to the ones that you're going to see in your your Alta Newton homework. Okay, so there's 3 listed here, and they're multiple choice. Okay, there's only one correct answer for each one. So I want you to pause the video, think about the relationships we just talked about between degree, turning points, and intercepts, and select the correct choice for each one, or the one you think is correct. And then when you're ready, unpause the video and we'll go over it. All right, so let's go ahead and look at these practice problems. On the first one, it says, determine which of the following most accurately describes the degree of f of x given that f of x has 3 intercepts. Okay, so if it has 3 intercepts, that means we ended up with 3 solutions when we're solving it, right, for our zeros or for our roots. So it says the first option is the degree is at least 2. Okay, so if we have a degree 2 quadratic, right, function, is that going to give us 3 intercepts if we have just an x squared? No, right? It's not possible to have an x squared and end up with 3 distinct intercepts, right? So we know it's not the first one. So then we look at the second one. It says the degree is at least 3. So if we had an x cubed, then yes, we could end up with 3 intercepts. So yes, it does need to be at least 3. So I'm going to go ahead and check that one. But we need to figure out why the last one's not correct, right? Because I said there's only one correct answer. Or you could circle these or color these in, whatever, it doesn't matter. Here it says the degree is at least 4. Now, it is possible to have an x to the 4th function and to get only 3 intercepts, right? But that's not what this is saying. This is saying that the degree has to be at least 4, which is not true, right? Because we could get 3 intercepts from having just a degree 3 polynomial. So that's why this one's incorrect, right? All right, so let's look at number 2. This one says, determine which of the following most accurately describes the number of x-intercepts that f of x has, given that f of x has a degree 5 polynomial. Okay, so it's a degree 5. That means we have an x to the 5th power. Okay, so it says f of x has at most 4 x-intercepts. Okay, so we're talking about the maximum. If you see at most, we're looking at the maximum. And remember, the degree and the intercepts have something very much in common, right? The maximum number of x-intercepts that we can get is equal to the degree. So as soon as you see all these words at most, you know you're talking about the maximum number of x-intercepts. And since this is a degree 5 polynomial, then the maximum number of intercepts we can have is 5. Okay, so this would be our middle choice, that it has at most 5 intercepts. Okay, all right, and then let's look at this last one. It says, determine which of the following most accurately describes the degree of f of x given that f of x has 4 turning points. Okay, so remember, when we're talking about turning points, we can have at most 1 less than the degree of that polynomial. So if we ended up with 4 turning points, remember turning points are like in between those intercepts. So if we ended up with 4 of them, that means we need one more intercept than 4, which would be 5. So the degree would have to be at most 5. Okay? All right. So hopefully that made sense. So now that we know our end behavior and we know what's happening at our intercepts, right? How many we can have, how many turning points we can have. Now we're going to look at actually solving for X and Y intercepts. So on the next page, we have our finding X and Y intercepts, and I'm not going to read through all of this because we've done X and Y intercepts before, right? We know to set the opposite variable equal to 0 and solve. We've done it with straight lines. We've done it with linear functions of straight lines, right? And then we did it with quadratic equations and quadratic functions. So now we're just looking at those higher order functions, but it's still the same idea, okay? Remember, they should always, always, always be written as ordered pairs because they represent points on a graph, okay? So let's go ahead and look at our examples here. It says find the X and Y intercepts of the given function. So I always start with a Y-intercept because I think it's a little bit easier to find, pretty much always. So our Y-intercept, we're going to set X equal to 0, okay? So if we take this Y, or this function, remember f of x is the same thing as y. So I'm going to write it with a y just so it's less confusing. So we have y is equal to, and then I'm just going to put a 0 in everywhere I see an x. So I have 0 minus 2, 0 plus 1, and 0 minus 4. So as I plug in all my zeros, what I really end up with is just -2 times 1 times -4. So when I multiply all those numbers together, what I end up with is a positive 8. Okay, so what this means is that my function will cross the y-axis up at y equals 8, but we want to make sure that we write it as an ordered pair. So we plugged 0 in for x and we got 8 out for y. So this is going to be 0, 8 as our y-intercept. Okay, so now let's look at our x-intercept. To find our x-intercept, now we're going to set y equal to 0. Okay. Now, y, again, remember this is just f of x. So basically we're setting f of x equal to 0, which means we're just setting this whole function equal to 0, right? So we have x minus 2 times x plus 1 times x minus 4 equal to 0. And the good thing about this example is it's already all factored for us. So remember when we were factoring to solve, we had to do some product or grouping or whatever factoring method we used. And then once everything was factored out and equal to 0, then we just set each of these equal to 0 and solve. Now, I'm not going to write out all the little equations because I feel like at this point we should be able to solve them. If you get to one that's a little bit tricky or not easy to do in your head, then you can always set it equal to 0 to help you solve it. But if I set x minus 2 equal to 0 and solve, I'm going to end up with x equals positive 2. If I set x plus 1 equal to 0 and solve, I'm going to end up with x equals negative 1. And when I set x minus 4 equal to 0 and solve, I'm going to end up with x equals positive 4. Okay. Again, don't circle your answers here. They're not done because these are intercepts. So we have to write them as ordered pairs. So this is going to be the ordered pair 2, 0, negative 1, 0, and 4, 0 because these are x-intercepts. Okay. Hopefully not too bad. Bringing back old memories of intercepts. All right, so let's look at a couple more and then I'll have y'all try some. So on this next one, notice again, we're going to start with our y-intercept because it's always the easiest one to find. And to find our y-intercept, we're going to set x equal to 0. So that will give me y is equal to, putting in a 0 everywhere I see an x is going to give me 0 cubed minus 5 times 0 squared minus 0 plus 5. So basically any term that had an x here is just going to turn into a 0, which is going to leave me with y equals 5. And then we want to make sure that we write it as an ordered pair. So that would be 0, 5, because we put 0 in for x and we got 5 out for y. Okay. So now let's look at finding our x-intercept. And this one's not factored for us, so we're going to have to do that ourselves. When we solve for the x-intercept, we're setting y equal to 0, or basically f of x equal to 0. So the whole function, x cubed minus 5x squared minus x plus 5, is going to equal 0. Okay. Now this is a 4-term polynomial. And remember, when we need to factor 4-term polynomials, our method is grouping. So we're going to go ahead and group the first two together, group the second two together, and see if we can get this factored out. So on the first two, I can take out an x squared. So if I take out an x squared, I'll be left with x minus 5. And then from the second pairing, I can factor out a -1, which will leave me also with an x minus 5. So now that they both have that x minus 5 quantity, I'm going to take it out, and I'm left with x squared minus 1. Okay. Now from here, you could go ahead and solve it, but I always encourage you to factor it if you can. One, because it gives you extra practice on factoring, and two, it may be easier for you to recognize than solving and having to remember plus or minuses and things like that. So here we have an x squared. So potentially this could go further, right? Now I only have 2 terms. So to factor with 2 terms, I'm looking for a sum or difference of cubes, which I know this isn't a cubic, right? Because I have a squared. Or I'm looking for a difference of squares. So I just have to look and make sure, like, are my 2 terms perfect square terms? So this one is, right, because I could square x and end up with x squared. And 1 is also a perfect square because I could square 1, right? 1 times 1 is 1, so it's a perfect square. And because it's subtracted, I know that this is a difference of squares. Okay, and remember, a difference of squares, once we know what our 2 little bases are that are being squared, we do our first base plus or minus our second. So this is going to factor into x plus 1 times x minus 1, right? And then we have our other factor of x minus 5 still here on the front, and it's equal to 0. So now that we have it completely factored as far as we can go, now we just solve each factor, okay? Just like we did on the last one. So when I solve this one, I'll get x equals positive 5. When I solve this one, I'll get x equals -1. And when I solve this one, I'll get x equals positive 1. And then we just want to make sure that we write those as ordered pairs. And I'm going to write them over here to the side because I'm kind of squished down here. So we end up with 5, 0, -1, 0, and 1, 0. Okay, not too bad. Okay, I'm going to bring up one more problem that's a little bit of a blast from the past. See if we remember one of our factoring techniques from a little ways back. So let's look at this next one. And when we first look at this one, we think, wow, that's ugly, right? Because it has an x to the 5th, which we're not used to dealing with, and x cubed, and it just seems kind of funky. But we're not going to get scared. We're first going to boost our confidence by finding the y-intercept because it's always easy. So the y-intercept, we're going to set x equal to 0. So I have y is equal to 0 to the 5th power plus 3 times 0 cubed minus 10 times 0. So when I plug everything in, there's an x in every term. So when I plug 0 in, it just becomes 0, right? And then we write it as an ordered pair. So 0, 0. And now that we have our confidence up a little bit because we easily found the y-intercept, we're ready to go ahead and move on to the x-intercept. So x-intercept, we're going to set y equal to 0, or in other words, we're going to set the whole function equal to 0. So we have x to the 5th plus 3x cubed minus 10x equals 0. And I want to factor this. So because I'm not used to working with the 5th power, I'm really hoping that, I can take that down a little bit. And I can, because the first step of factoring always is to look for a greatest common factor. So notice they all have an x in common. So I'm going to go ahead and take that x out first, which leaves me with x to the 4th plus 3x squared minus 10 equals 0. Now, this looks like a little bit better, right? We've seen x to the 4th before, and we've seen 3 terms. 3 terms, usually we do sum product, right? But our sum product chart is intended for quadratic functions or quadratic polynomials, right? So I would really prefer this to be an x squared, right? And this to be an x to the 1st power, but it's not. So do you remember when we went over how to factor higher polynomials by using substitution? That's what we're going to go back to doing here. So what I want to do is I want to write this as a variable that's just to the 1st power. So I just want to replace that x squared with a different letter. So let's just say, let's let y equal x squared. okay? Because if y is equal to x squared, I could write this as 3y, right? And then if y is equal to x squared, x to the fourth is just x squared squared, right? So I could write this as y squared. So I'm just substituting in a y so that I can end up with a y squared plus 3y minus 10. So a variable that has a squared term to the first term and then a constant, because this is what I can use the sum product chart for. So I'm going to go ahead and factor this. My sum would be my middle coefficient here, which is positive 3. And my product would be my first coefficient, which is 1, times my last, which is negative 10. So something that I can multiply to get negative 10, that I can combine to get 3 would be 5 and negative 2. Okay, so now that we have our pairing, remember normally we take this and replace the middle term, but because my leading coefficient here is a 1, I can go ahead and use the shortcut. Yay for shortcuts. So this factors into y plus 5 and y minus 2. Okay, so that's good. Yay, I got it factored. But remember, our original problem, we're solving for x-intercepts, right? So I really don't want y's in here now that I have it factored. So what that means is now that I have it factored, I need to go ahead and plug back in what we let y equal. Y was representing x squared. So now that I have it factored, I need to go ahead and plug back in for y. Okay, so whatever y was, we need to plug it back in. So I'm just going to rewrite these two factored quantities that I got here, but instead of y's, I'm going to go ahead and put in my x squared. So this means we have x squared plus 5 and x squared minus 2, right? And then don't forget to bring this greatest common factor down, okay? Equals 0. Now, we still have x squareds, so there's potential to keep going, right? So I'm going to double check, just like we did on the last problem, to see if I have a difference of squares. This one's not a difference, it's a sum, so we know we can't factor that. And then this one is a difference, and x squared is a perfect squared, but 2 is not a perfect square. So I can't actually go further with factoring. So this is as far as I can go with factoring. Now I'm going to go ahead and set each factor equal to 0 so I can solve. When I set x equal to 0, I get x equals 0. Okay. When I set x squared plus 5 equal to 0, I get x squared equals, now when I move that 5 over, it becomes a negative 5, right? And then to solve this, I can get rid of the square by taking the square root. And remember, when we solve by taking the square root, we have to make sure we use plus or minus. So I get plus or minus the square root of negative 5. And then when we have a negative 1 underneath our radical, that gives us a complex number, right? We can bring that out as the imaginary unit I. So we have plus or minus I square root of 5. And then I want to solve my next one. So I have x squared is equal to, when I move that 2 across the equal sign, it's going to become positive. And then again, just like the last one, I can solve by taking the square root. Don't forget your plus or minus. And the square root of 2 does not simplify, right? It's like 1 point. So we're just going to leave it as a square root. We're just going to leave it as a square root, okay? So remember, going back to what we did, what are we doing here, right? We're solving for the x-intercepts. So when we solve for x-intercepts, we're looking for those ordered pairs that we can graph. And if you look at the answers that we got here, we actually can't graph this one, right? Because it has an I, it has that imaginary unit, and there's no way on an XY coordinate system to graph anything that has an I in it. So I'm going to go ahead and just say here, cannot graph imaginary or complex, right? Or complex intercepts. Okay. Cannot graph imaginary or complex intercepts, which means that we're not going to worry about this one. Now I'm crossing it out here because we're specifically looking for intercepts. If this was just an equation and it said solve for x, yes, plus and minus 5i does solve the equation. However, it does not give us an x-intercept because it's not a real number that we can graph. Okay, so the only x-intercepts that we get from this problem would be 0, 0, which we got from our greatest common factor, right? And then the two x-intercepts that we get from that last factored quantity, which is negative square root of 2, 0, and positive square root of 2, 0. Okay, so those are our x-intercepts. All right, okay, so I believe there is two, yes, there's two for y'all to try. So go ahead and pause the video and find the x and y intercepts of both problems. Be sure to write them as ordered pairs, and then go ahead and unpause the video when you're ready to go through them and check yourself. All right, here we go. So let's look at the practice problems. Our y-intercept of number 1 should give us a 0, 0, because when we plug in 0 for x, it's just going to equal 0, right? Make sure you write it as an ordered pair. When we look at our x-intercepts, we're going to set the function equal to 0, right? Because for x-intercepts, y is 0. And we can take out an x squared, right? They all have at least an x squared. So we're going to factor out the x squared, which leaves us with x to the 4th minus 3x squared plus 2. And then, just like I did on the last example, we want to go ahead and use substitution to create something that looks like what we're used to dealing with in our sum product chart, right? So here we use y. I think in another video I use w. It really doesn't matter what letter you use, but we always want to replace that middle one, right? Because if we can replace that middle one, it will become just a letter to the first power, and this one will become that letter squared, okay? So I'm going to let y equal x squared. So when I replace my x squared and my x to the 4th, I'm going to get y squared minus 3y plus 2. And now this is something I can use my sum product chart for. My sum's going to be -3 and my product +2. So I need to use -2 times -1 to multiply to a +3 and -2 minus 1 to add to a -3, right? And because my leading coefficient is a 1, I can go ahead and use my shortcut. So I'm just going to plug those numbers into my factored quantities. So this will factor into y minus 2 times y minus 1. And now that I have it completely factored with my y, I've done all that I can do with y, right? So now I want to go ahead and plug back in for what we originally allowed y to equal, which is x squared. So I'm just going to take my two quantities, y minus 2 and y minus 1, and put my x squareds back in. So I have x squared minus 2 and x squared minus 1. And then don't forget to bring down that greatest common factor and write it here on the top, okay? All right, and then from here, I always check to see if I can factor it further. Even though both of these can be solved using the square root property, I always look just to see if there's maybe a difference of squares. So x squared minus 2 is not a difference of squares, so I'm going to leave it the same. But x squared minus 1 is a difference of squares, right? So this one will factor into x plus 1 times x minus 1, and then we just solve all of our factors by setting them equal to 0. So we set x squared equal to 0. That gives us a 0 as a solution or as an x-intercept, right? X squared minus 2, again, we move that 2 over, take the square root of it, so we get plus or minus the square root of 2. And then on these last two, I should get a +1 and a -1. Now, if you solve this by just setting x squared minus 1 equal to 0, just remember when you take the square root, you need to put that plus or minus, because if you don't, you're going to miss out on one of these answers, okay? And then just write all of your solutions down here that are real numbers, which they all are here. We don't have any imaginary numbers. Make sure you write them as ordered pairs, okay? All right, and then let's look at the second one. The second one is actually even just a little bit easier, right, than the first one. The second one was when we plugged in 0 for our x, right, we still have numbers left in our quantities, which is -2 times 1 times -4, so we end up with a +8. Don't forget to write it as an x-intercept. And then for our x-intercept, we set our whole function equal to 0, and then we just solve each one. So this one was already factored for us, which is much easier, right? So the first factor gives us x equals 2, second factor gives us x equals -1, and the last factor gives us x equals 4/5. So go ahead and leave that as a fraction. Don't turn it into a decimal unless the instructions in Newton tell you to do so, okay? All right, and then we write all of those as ordered pairs, all right? Okay, so here's where we're at. Now we know how to find the number of intercepts and turning points. We know how to solve for X and Y intercepts. Now what we're going to look at is the behavior at those intercepts. And the way that we find the behavior at those intercepts is by looking at the multiplicity, okay? So I want to go ahead and, oh, that was y'all's practice problem. Okay, so I want to go ahead and look at the multiplicity. Now, we're going to assume that we factored out a function, okay? We have something like f of x equals some factor times some factor times some factor, right? However many factors we have, okay? Now, the numbers are the exponents that we have up here, p, q, r, s, okay? Whatever those numbers happen to be. Now, some factors, we may only have one factor, right? Like the ones we did up here. Notice each of these factors, I had one copy of that one copy of that one copy of that one, right? But sometimes we have multiple copies, which we call multiplicity, right? So what we're going to do is we're going to look at the multiplicity on the factor, not the x, on the factor that our exponent or that our x-intercept came from. Okay, so here they gave us an example. So it's kind of like we're assuming this first one is x minus h. Okay, if we were going to start setting all of these equal to 0 and solving, if I set x minus h equal to 0, I would end up with x equals h, right? Which would give me the x-intercept h comma 0. Okay, so we're just saying this is one of our factors and we have p copies of it. Okay, however many that happens to be. So the way that we determine our behavior at those intercepts is we look to see if the number of copies is even or odd. Okay, if p is even, or if we have something like a quantity squared or a quantity to the 8th, or maybe we just have a leading coefficient out here. I mean, sorry, not a leading coefficient, greatest common factor out here, right? Maybe we have x to the 7th out front all by itself. Okay, that's the multiplicity of that factor. So if the multiplicity happens to be even, then we know when we graph it, our graph will only touch the x-axis. Okay, it will only touch. It won't cross. So what that means is if I have a graph and let's say here's my x-intercept, that means that the graph may come down and touch it and bounce back up, or I may have an x-intercept that's coming from the bottom and it may touch and go back down. Okay, something like that. So it's not actually crossing the x-intercept or the x-axis. Okay, now if my number out here happens to be odd, right? If p happens to be odd, like this case, like we have an x to the 7th as a greatest common factor, that's odd. That's when our function will cross the x-axis at that intercept. Okay, so let me show you kind of what that looks like. So here's our example, and we want to find all the zeros and their multiplicities and then state whether it touches or crosses. Now you're going to have a worksheet coming up. It's not on this section, but it's in the next maybe 1 or 2 sections to come. And on that worksheet, I'm going to expect you to work it like I'm about to show you. So make sure you write down what I have here. Okay, so the first thing is we want to find the zeros. So if I solve for this, I'm going to get x equals -3, right? Now I want to find the multiplicity of the factor that -3 came from, which is this one, right? So my multiplicity for that first factor, well, if I look at the exponent, I only have 1, right? I only have 1 copy of that factor. So multiplicity is 1, I only have 1, and 1 is an odd number. So because it's odd, I know that my graph is only going to cross at that x-intercept, okay? So it's going to cross at the x-intercept, and I don't want to write it as x equals -3. I want to go ahead and write it as the x-intercept -3, 0. Okay, so this is what I'm looking for. I want to see that you found the 0, that you stated the multiplicity, that you then said, okay, based on that multiplicity, it either touches or crosses, and then you write that 0 as an x-intercept. Okay, if you don't write all of this when I grade your worksheet, you're going to miss points. Okay, so let's look at the next one, x minus 7. So if I solve that, I'm going to get x equals +7. And the multiplicity from that factor, if we look at the little exponent up here, it's cubed, right? Or it has multiplicity 3. So multiplicity 3 is also odd. So this one is also going to cross at the intercept 7, 0, right? Okay, so that's my information for that one. And then I want to solve this last one, which will give me x equals a positive 12. And then I want to write the multiplicity of the factor that came from, okay? Notice we're not looking at the power of x. We're looking at the exponent on the factor that it came from, okay? The multiplicity here is 4, which is even, which means that our graph is going to touch at that x-intercept, and that x-intercept is 12, 0. Okay? Kind of makes sense? Okay, so we can take a function and actually identify the zeros and state whether they touch or cross based on their multiplicity, or we can actually figure out what the multiplicities of the factors might be based on a picture if we're given the graph. Okay, so I'm going to go ahead and look at one like that. So on this next page it says, use the graph of the function of degree 6. Okay, that's important. Well, the degree is always important, right? That's what this section's been about. All right, so this is a degree 6 function, okay, and it's shown below, and we want to identify the zeros of the function and their possible multiplicities. Possible, okay? So we may not be 100% accurate on the exact one, but we should be able to come up with what it might possibly be. Okay, so let's just do this one the way we did the last one, and then we'll talk about the possibilities. Okay, so first of all, looking for x-intercepts. When I look for x-intercepts, I can see I have an x-intercept right here at -3. So I'm just going to write out x equals -3. Now, does the graph touch or cross at -3? Well, I can see it's up here positive, and it comes down at -3, and then it stays positive, bounces back up, right? So it doesn't actually cross, so I'm going to say it touches. Okay, so what that tells me is that this one has to have an even multiplicity because it only touches, okay? And I'm going to write it as an x-intercept, which is -3, 0. Okay, so that's my first one. Our next x-intercept is here at -1. I'm just going to go ahead and write x equals -1. And notice it crosses the x-axis at -1. So if it crosses, that means that we should have an odd multiplicity, right? And it crosses the graph. I'm going to write it as the x-intercept, -1, 0. And then our last x-intercept over here is at +4. Okay, so we have x equals +4. Now I will warn you, it kind of even got me because I was working this homework assignment just to make sure I knew what all was getting popped up on you guys. Wow. On you guys' end, and there was a lot of multiple choice questions that came up for me. And so when I was doing these multiple choice, they would give me ones like this, and it would look good. It'd be like, oh, there's a 0 at -3, -1, -4, and I'd be like, yeah. And I'm like, oh wait, no, not -4, +4. So be sure when you're looking at those multiple choice problems, you're really looking at not only the signs, but also the multiplicities very closely, okay, so you don't get the wrong one. All right, so this one at x equals 4 is crossing the x-intercept, or crossing the x-axis. So if it's crossing, we know it has to have an odd multiplicity, right? And we're going to go ahead and write that as an x-intercept, which would be 4, 0. All right, so we've identified all of our zeros. We know if their multiplicities are odd or even based on if it touched or crossed. So now we want to look at the possible multiplicities. Okay, so let's think about this. If this is a degree 6, that means when we add all of our multiplicities up, it should equal 6. So let's start down here. Let's say this one has to be odd. So I'll write over here, possible multiplicities. Okay, so let's just say, let's pretend this one has to be odd, right, because it has to cross. So let's say maybe that one's multiplicity is 1. Let's say we have 1 copy of that factor, right? And then this one also needs to be odd. So let's just go ahead and say we have 1 of that factor. So we've used 2, right, of the 6 that can come from a degree 6 polynomial. So if we've used 2 of them, that means there's 4 left over. So it is possible to have 4 of this one, right, because it has to be even. So this is one option for the possible multiplicities. This one could have come from a factor that was to the 4th power, and we could have just had one of each of these, right? But let's say this wasn't to the 4th power, right? Well, the only other even power that's less than 6, because we can't use 6 because that wouldn't leave any for these two. So the only other even multiplicity less than 6 that isn't 4 would be 2, right? So that was one option. So this one could be maybe multiplicity 2, right? So if this one's multiplicity 2, that takes 2 from our 6 possible degrees, right, or powers of x. So that leaves 4 for these other two. Now, I can't just split it down the middle and say, well, that means there's 2 of this one and 2 of this one, right? Because if I do 2 of this one, that's not odd, that's even. So instead of doing 2 and 2, I would have to split it up 3 and 1, right? So this one could have 3 copies and this one could have 1 copy. Or it could be the reverse, right? So I'm going to go ahead and write one more option here. Is that this one is 2 and then this one's 1 and this one's 3. Okay, does that kind of make sense? So we know that because based on this graph, it has to be one of these 3, right? Because this is the only possibilities for this first one to have even and the next 2 to have odd. So when you're looking at these problems in your homework, you need to be checking a couple of things. One, when you look at your multiple choice selections or choices, right, you need to make sure that the signs of the zeros are correct. Because sometimes they'll throw in wrong answers where maybe this would be a +3 and then -1 and everything else will be correct, but this will be a +3. So pay attention to signs. The second thing is pay attention to even or odd multiplicities. Okay, so if it needs to touch, then it better be even. If it needs to cross, it better be odd. If all of those things line up, if they have the correct zeros and the correct multiplicities, then the last thing that you need to check for is to make sure if you add all those multiplicities up, do they total the degree of your function? Okay? All right, so there's 2 practice problems for you to try using your newfound knowledge. So go ahead and pause the video, and then when you're ready, play it back. Okay, here we go with the practice problem. So number 1, this was easy. This one was already factored for us, and we can easily see the multiplicities on each factor just by looking at their exponents. So the first one gives us the 0x equals 3. So as an ordered pair, that would be -3, 0. It has multiplicity 1 because I only have 1 copy of that factor, which means it's going to cross at that x-intercept, right? Similarly, we get x equals -10 for this one. Has multiplicity 5, which is odd, so it's going to cross. And then make sure you write that -10 as an ordered pair for the x-intercept. On the third factor, when we solve it, we get x equals +4. That factor that 4 came from was squared, so it has multiplicity 2, which is even, so it touches at 4, 0. Okay, and then our last one, we have only 1 copy of that, so multiplicity 1 means it crosses at that last x-intercept, which is 8, 0. Okay? All right, so far so good. Number 1 was the easy one, right? All right, let's look at number 2. So number 2, when we look at this, we can see, okay, at -5, we need an odd multiplicity because it crosses, right? At -1, we need an even multiplicity because it only touches. And at 3, we need an even multiplicity because it only touches. So we're first of all going to make sure that we have -5, -1, and +3 for our zeros. So when I look at these multiple choice options here, notice these all list -5, these all list -1, and these all list 3. So far so good. All of our zeros match up. Then I need to make sure that at -5, we're choosing odd multiplicities. So if I look, notice they're all 3. Well, if they're all 3, they're all odd. So that one's not going to help me out. So now let's look at -1 and 3. They both need even numbers. So at -1, look, they're giving us all even options. And at 3, they're giving us all even options. So that didn't eliminate any for us. So what I really need to look at now, the only thing I have left to look at, is that this represents a degree 9 polynomial. Okay, now if it's degree 9, that means when I add up all my multiplicities, it should total 9. So when I look at this first one, I have 3 plus 2 plus 4. Well, 3 plus 2 is 5 plus 4 is 9. So that one works. So that's one of my possible multiplicities. On the second one, I have 3 plus 4, which is 7, plus 2, which is 9. So that one works. But if you look at totaling the next ones, this one actually totals 11, and the last one actually totals only 7. So because these multiplicities did not add up to the degree of our polynomial, we know that those are not possible choices to represent it. Okay? All right, so that is the end of this section, which was local behavior of polynomial functions. So you should now be able to complete this assignment in your Knewton Alta homework. And if you have any questions, please let me know.